Welcome to Module 9. So this is normally what I'm doing in the last week of classes. Um, but that's okay. I think on the online system, Module 10 will be going in somewhere. So wherever you put in Module 10, that's where it goes. But anyways, Module 9, we are looking at the photogrammetry. So what we're what we're really looking at in this module is an introduction to remote sensing. So you'll be taking remote sensing next year in the fall with me. Well, probably me. I hope so anyway. um, so I'm taking it with me, and, and but this really starts with it. So this gives us the basis of like the geometry of it. It gives us the basis of what is aerial photography. It gives us how do we see in 3D with aerial photos? How do we identify features? There's a lot of questions that get answered about aerial photography, and being able to identify things from a sensor that is not actually physically on the world. So the first part is the parts of the electromagnetic spectrum. So this is the electromagnetic spectrum. Usually I stand there and let everybody tell me what is on the electromagnetic spectrum. So there's a few things that I want to point out is that really everything on the electromagnetic spectrum we can use for images except for radio. Radio is the only one that we really can't use for imaging. So gamma rays we use a lot for like brain imaging, and you can also use gamma radiation for all kinds of different stuff. You can do brain surgeries without needing to cut into the skull with gamma radiation. So it's really quite a powerful medical tool. When we try to do imaging with gamma radiation, I think the non-destructive testing does use it a little bit, but again, you have to be really close to it or close to the object if you're going to be using gamma. The reason you have to be so close is because the short wavelength of it, it tends to scatter very quickly and scatter away. So it will hit like an air molecule and it scatters. So it's something just to be um, aware of anyways. Then the next one is X-ray. You guys should be all familiar with X-ray. What's kind of cool about X-ray is that it actually detects the density differences between different materials. And so that's why X-ray works so well, like looking at bones, because it looks through soft tissue and it sees the change in density at the bone, and then it will show the bone itself. Then there's ultraviolet. So ultraviolet is well, from the sun usually. You can also manually create it as well. But ultraviolet, this is more on, we use this kind of as a passive sensor, and I'm going to be getting more into too much detail if I get really into it. But ultraviolet is a very useful type of light because it does help our bodies produce vitamin D. It also does sterilization for us. So if you work in the sterilization technician world, you use ultraviolet a lot. So it is used, it's very practical in many ways. And you use it for imaging as well. So we use ultraviolet to create images. It tans your skin, everything like that. Then we have visible light. So visible light is is what our eyes see. That's really all it means. So it is like a tiny part of the electromagnetic spectrum, because the spectrum goes to infinity, of course. So everything's tiny, but in like what we work with on this earth, visible light's really, really small. And so our eyes really don't see a whole lot. Even if you're colorblind, you still really are seeing in the visible spectrum because we can't see infrared. We can't make out shapes in the different parts of the spectrum. So that's visible. Then we have infrared. So infrared really covers a big range of values. So if you look at the lower right hand corner, you're going to see that there's 5 sections that kind of fall in there. So we have near infrared, which near infrared is a one part of the spectrum. This is what you use to change the channel on your television. It also tells me how healthy vegetation is. because it reflects back very, very strongly when you have really healthy vegetation. So we use that for a lot for vegetation applications. Shortwave infrared tells me a lot about organic materials and soils. Again, these two have nothing to do with heat, right? So the shortwave infrared looks at organic materials, looks more at like soil-based stuff. So I can see moisture in soil as well with it. And it provides that mining application if you go into that area. Now, I don't necessarily, every book is going to label thermal infrared differently. So in what I know, mid-infrared, mid-wave infrared is not thermal because it does not create heat. So mid-wave infrared is actually looking at solid rock. So it helps us identify between rocks. It helps us identify between man-made rock types like cements and such. So maybe that's an infrared, but if I am receiving mid-infrared radiation, I am not receiving heat. So I don't necessarily agree with the diagram, but it has a really good breakout of what the infrareds are. Then we have something called long-wave infrared in this diagram, which is also known as thermal. Now, thermal, again, every book is so different. It's ridiculous. Like, there's never these numbers. I never tell anybody to memorize these numbers because it's useless. Because the next textbook you look at, the next diagram you look at, is going to be totally different. So except for the visible spectrum between 400 to 700 nanometers, that's the only one that's like the correct. But in here, these boundaries are really fuzzy, really, really fuzzy. So long wave infrared is often like more so in the far infrared as well. And so this is thermal. This is like whole section in here, like kind of the midway is is a thermal. And so that is the heat. That one identifies heat, does not identify anything else other than heat. So it does like look at emissivity. There's a whole big thing that comes with it, but that we'll discuss that next year. But don't don't separate long wave radiation from thermal because that's really what it is. We often talk about that like when energy comes into the atmosphere and the atmosphere absorbs it, it actually releases it as long wave infrared. So then we end up with thermal infrared in the atmosphere from that. And then there is the far infrared. Far infrared is not thermal either. Um, from what my knowledge is, again, I like the diagram, but it's not perfect. So the far infrared is almost of a microwave type, and microwaves don't actually generate heat. That is not what they do. And thermal, the term thermal is the actual like detection of heat. Okay, so microwaves do not create heat. And far infrared is kind of a blend, I guess, between thermal and microwave, but it is not heat. Far infrared, it drives me crazy when you try to buy something and they're like, oh, it uses the far infrared spectrum. And it's like, no, it does not. Because if you're using far infrared, it is actually going into the microwave area. And it's like the kind of the buffer between thermal and microwave, and it does not create heat. You cannot detect it on a thermal camera. So it's if you go over and you touch something that is considered like to reflect far infrared, all it means is that it's reflecting your own body heat. And you're like, oh, it's warm. It's like, yeah, it's because your hand's warm. So it's reflecting that heat. Anyway, so just to keep that in mind, and that's really all the far infrared is. It's not actually a true component of it, like of thermal in what I have been taught. It's kind of a weird fuzzy boundary. So some books like this one say yes, it is part of thermal. Some books say no. So it depends on how you investigate it. So then the next spectrum is microwaves, and actually this is my specialty. I'm actually a microwave expert. That's my background. I love working with microwaves. I think that it's like the coolest thing ever because there's so much you can do with it. There's a whole bunch of different bands of microwave. So you can use microwaves from everything from like GPS to like sending radio signals to using cell phones to using Wi-Fi to detecting crop types to determining the thickness of ice in the Arctic to seeing through clouds, to looking through walls. Like you can use microwaves for so much. GPR is microwaves, like ground penetrating radar. That's all microwaves. And what I'm doing right now in my PhD is I'm using microwaves to look at tumors in breasts and seeing how well does the treatment actually affect that tumor. So microwaves are crazy, crazy things. Like they are so incredibly powerful. They're not just for cooking food. That's only one really tiny band of the microwaves, and I've got long stories about that. But I have gone in front of microwave systems many, many times in my life, and like ones that are like directed microwave systems that are like other bands other than the cooking band, and I have not cooked myself to death. I'm still operating pretty well, I would say. So just something to keep in mind. In fact, a natural emission of microwaves is snow. So every time you walk outside in the snow, you are walking outside into like being totally bombarded with microwaves. So if you're going to tell me that you cook from going out in snow, then let's have a conversation because I think you might need to go see a doctor. Anyways, so that's microwaves. And then there's radio waves, and the radio waves are long waves. We don't do any imaging with radio waves. They're just too long. The object that you are looking at has to be greater than 26 meters. And like really at that point, the resolution of radio waves is so poor that it doesn't make any sense. Perhaps in astrophysics, they might use radio waves for imaging. And it's possible. I haven't actually looked into it, but if you know anybody in astrophysics, you can ask them and say, hey, do you guys use radio waves for creating images? Because they might, because they're looking at planets rather than looking at features on the ground. So just something to keep in mind with the electromagnetic spectrum. So gamma rays have the shortest wavelength and they have the highest amount of energy. So really anything from like ultraviolet down is cancer causing. Anything from like infrared up is generally harmless because it's such a low energy. So the next thing is listing the characteristics on aerial photos. So this is the electromagnetic spectrum is what creates the photo. So we can have color photos, we can have all kinds of stuff, and I think I get into that later. But what's really important is what is on the aerial photo and around it. So here we have an aerial photo, and we don't tend to get a lot of analog photos anymore because digital is just cheaper to be able to produce and work with. It used to not be that way. So if you have to work with historical data, you got to know this. But this is also, all of this information you're going to find in the metadata of your aerial photo. So I want to ensure that you know what these different parts are, and some of it actually shows up on the photo itself when you pull it into your system, whatever software you're using. So here we have basic ones you're going to see is altimeter. So the altimeter tells you how high you are flying. And so down here you can see a little dial that's saying how high they're flying. You're going to see the date. So the date that you've gone out to do the survey. So here you can see here there's a date. There's also a time. So you have the clock that's showing the time. Then you have a focal length. And the focal length tells me how far away from where all of the light comes and connects together to where the film is. So that is considered a focal length. And we'll get more into detail when we get to the diagrams and the geometry. But that focal length is essential. And the reason why it's so essential is because it does allow us to calculate scale. So and do measurements on the actual photo itself. The next one is fiducial marks. So fiducial marks are little crosses at the different parts of the aerial photo. Now this one only has 4, so it has one on each end and then either side. And then there are often fiducial marks that you'll find in the corners. So the aerial photos I have of SATE, they have fiducial marks in the corners. Now the reason why they do fiducial marks is because it tells me where the center of the image is. And the center of the image is known as the principal point. That's the center of the image. That's not the center of the ground. That is the center of the image. So that's a little confusing, and we'll talk a little bit more about that. But the principal point here is the center of the image. And it allows us to be able to calculate errors of the photograph so that we can actually correct for those errors on the ground and then have a better scale, which is really helpful. We're going to have a whole bunch of lens information, so you're going to see things like serial number, negative number, roll and frame number, project number, etc., etc. So there's all kinds of stuff that have to do with the lens. Well, I mean, obviously project number has nothing to do with the lens, but it's not there. Next thing is airport. So this one, this example here, it's not showing which airport it comes out of, but here you'll see they might be written in here where it's coming out of. And then we have latitude and longitude, so it's the location that it is located at. Again, we don't see it on this particular one, but on the newer images, they're all going to say where the center of the photo is. And then it's going to have a predicted scale. Sometimes it has that, sometimes it doesn't. The predicted scale says, I want this, the aim of this project is to have the scale at 5,000 meters. That does not mean that the scale is 1 to 5,000. Sorry, I've totally said that scale wrong before. That the estimated project scale is 1 to 5,000, and so therefore we would not do. We're not going to take that as my scale because it's what they want. It is not what it is. So when we go to correct for all these images and do all that work, we actually have to figure out what the scale is of that image so we can match it with the next image, because we're going to have to match them at some point. So that predicted scale is merely like this. You should be close to this number. You might be off by a few hundred, right? Like 1 to 4,500 to like 1 to 5,500. That would be normal. But if you're like 1 to 10,000, then there's something really wrong. So it's just something to help you keep you with your calculations. So one of the things I didn't really mention, didn't point out here, we have the focal length. So you can see the focal length here. It's in millimeters. Generally, they're about 150 some millimeters. And so the longer they are, the more like zoomed in it is, etc. So that's aerial photo characteristics. So those are the things, the metadata that you're going to find when you deal with an aerial photo. And again, they may not be 100% totally required for math, but they might be really required to know what's going on, because it allows you to catalog it, allows you to file it away, it allows you to retrieve it very easily. If there's an error, you can find out, okay, I used this lens, what's going on? Maybe the lens needs to be calibrated or something. So that's what that information comes from. So the next video, we'll be getting into some calculations with the scale of the aerial photo. So you can move on. When you get a chance, you can move on to Objective 9.3.